Hello, I am NARAYAN PRADHAN, working as a scientist in Indian Association for Cultivation of Science. Today we are going to talk about one of our recently published perspectives in Journal of Physical Chemistry Letters. This is entitled Recent Developments of Metal Phosphides as OER Pre-Catalyst.
Hi, I am Anirban Datta, a graduate student of this lab. My research is focused on designing phosphide material for photochemical and electrochemical energy generation. Metal phosphides are one of the promising catalysts of today's era. Their hydrogen evolution reaction activity is widely reported, but their OER activity is limited. Though it is not new, it has been started way back in 1989, but it got attention to the researcher very recently.
The research on metal phosphide mostly restricted because of their synthesis difficulties. Being a synthesis group, we took these advantages for designing different metal phosphides. Among different methods, we adopted the XC2 phosphine generated method for the synthesis of these materials.
The advantage of this colloidal synthesis route is, in colloidal synthesis, you can have a better control over shape, size, phase of the nanocrystal, which are important part of catalysis. In a country like India, where many other phosphorus sources are not available, in this case, this XC2 mediated phosphine generation provides us the opportunity to explore the material in a cheap, economical way.
We synthesize metal phosphide in phosphine mediated methods where calcium phosphide treated with HCl gives a phosphine gas, and that phosphine gas has been forced to the metal salt, and as a result we get the metal phosphides. The flask contain calcium phosphide. Now HCl has been injected. Soon after the phosphine gas is generated. As you see, here is the phosphine has been carried out by argon and it is bubbled in the cobalt chloride solution. As a consequence, we get the cobalt phosphide.
However, synthetic achievements opens up many possibilities to tune their activity further. Among the various parameters, these are all well explored parameters. Conductive electrode fabrication. Growing the material on conductive substrate can boost the efficiency of the material. Cationic modulation. Insertion of secondary cation can drastically change the activity of the material. In several cases, manganese and iron incorporation into the lattice of cobalt phosphide boosted the efficiency of the material. Anionic modulation. Not only the cationic modulation, anionic modulation also plays an important role in the activity. For example, incorporation of oxygen in nickel phosphide and cobalt phosphide enhances the activity drastically. Phase of the material. Metal-rich phases showing more activity as the conductivity of the metal-rich phases are high. A direct comparison between monocobalt phosphide and dicobalt phosphide reveals dicobalt phosphide has much higher activity. While measuring the activity, we found a broad peak before or along with the onset potential, which indicate some irreversible oxidation is taking place. This prompts us to check our post-catalysis sample. XPS study reveals that the surface is converted to oxide or oxyhydroxide. HRTM of the post-catalysis samples also reveals the surface modification, and finally, in most of the cases, they found to be phosphide oxide core cell type of structure. Interestingly, their activity remain superior than their corresponding oxides.
When we look the future of these materials, our target would be designing new metal phosphides with superior OER activities. The main driving force of this work is my students. I would like to thank the director of this institute, the head of the department for the support. I would like to thank CSR and DST of India for funding, and thank you for watching the video.